Uh, okay, it is our second session, and on this second set of our midterm examination, again, I won't explain to you again strength and stiffness. It should be the same of the previous one. The second one, why do we need to determine the magnitude and principal stresses and principal strain? You may recall back to chapter 5. We use principal strain to predict the failure. Okay, you should start by explaining the principal stresses and strain are the maximum normal stress and normal strain. Okay, that's going to be typical knowledge for to say that for a given state of stress. Also strain on a given material point. We also consider the material point. Okay, and when the structure fail, it fail by a small point on the material, and then they can cause the failure of the material of the materials. Thus, we must determine them. We must determine them in order to predict the failure. And also the failure plane of the material. That is two things: failure and the failure plane. Okay, then coming to the next one, what's going to be isotropic and homogeneous material? I just said for homogeneous, every material point is the same, are the same. Material points they are the same, such as steel. Okay, you can put any point and it's gonna be all the steel. How about reinforced concrete? No, reinforced concrete is not homogeneous material. Timber also theoretically not homogeneous material. Okay, how about isotropic? Isotropic is material when you cut it in any direction and then you test it. Okay, you have very big material. You cut it in lateral direction. You cut it in longitudinal direction. All of them have the same mechanical property. Then, how about an isotropic? Timber also an isotropic actually, and also non-homogeneous. But in the big pictures, such as reinforced concrete, we consider the whole pictures of the reinforced concrete in the structure. So macroscopically, they can be considered to be isotropic homogeneous. And then Ajahn said, what going to happen to them? Okay, for the compressive force, if we have one, okay, that's going to be in compression. For isotropic, what you should have from the book, okay, the direction for isotropic gonna be in the different one, okay. For this one, the new pictures gonna be something from the blue to the black, okay, and this one starts from the blue, this one, the blue, and then to the black. So the pictures that you draw should be in the opposite direction, okay, and then for this one, isotropic and homogeneous materials. And then for this one, I didn't ask you. I didn't ask you. Okay. And then for the other one, we also have this one. If you should put it, since it is an isotropic, you may need to put more detail to show. It should have first, not every material point gonna be the same. And then when you cut it in one direction and you cut it in other direction, it won't be the same. Then when you put it in the compression, sure, it will not be the same. It should be something close to this one, but it's gonna be quite opposite. This one should have the pictures to be such as this one, and also maybe on this form, and may have shear deformation. Also, this one gonna be an isotropic, and then this one this one homogeneous, right? So this one, if it's homogeneous, the direction of this one may be just in parallel, because we putting it should be close to isotropic material, but the behavior gonna be something close to this one. It said this one may have this kind of direction, okay, and then what it says, this is going to be homogeneous. Actually, I should put it an isotropic and inhomogeneous material is should be like this one. This one should be inhomogeneous. But anyway, I should provide a benefit for you for this one.
Actually, my drawing is just
Yeah, something like that one. It's okay. It should have some different. The main thing gonna be this one. The deformation gonna be due to the normal stress only, and this one under the normal stress is may have normal strain and normal strain and shear strain occur. This one normal stress will provide only normal strain, but this one normal stress provide normal strain and then shear strain. That's going to be the main thing. Okay. That's going to be what you should have it based on the textbook that we have. I didn't ask you for this year. I will ask later next year. And you have passed it already. Okay, next. come to what we have over here. And I believe this one you should be good at it. Okay. On this problem, again, we have two force member and our two force members subjected to two forces. One is going to be P1 and then another one going to be P2. So this is P2 14 kilonewton, P1 31.5 kilonewton. The structure made by a given material having entering state strain diagram like this one, and the materials has the E already. So you don't need to measure the modulus of elasticity. Use this E. And then also the problem will work with the sigma sub y. Okay. And then the dimension of this one separate into two portions. The portion AB, this is 600 millimeter, and then the area gonna be 100 square millimeter. For the BC, this is 500 millimeter and smaller with the 50 square millimeter cross-sectional area. Then we are going to determine the total elongation. Okay, we start by first one. We got to the free body diagram, and then we will use equation of equilibrium to determine internal forces, and then we will use internal forces to determine stress equal to internal forces divided by cross-sectional area. Okay, then starting this one, let's put the reference axis to be x and y, and then you may cut the first one that's supposed to be for the BC, another one should be for the AB. Then we have the first one. Okay, this one going to be the free body diagram for the BC, and then we may also cut this portion, and then this is mainly for the section AB, and then this one subjected 14 kilonewton, and it is the axial force. So this one gonna be F sub BC, and for this one we have two forces, 14 kilonewton and 31.5 kilonewton. You will have internal force over here to be F sub AB, and then summation of F sub y equal to 0. F sub AB gonna be 31.5 plus 14. You will get 45.5 kilonewton. And then for this one, if you do the summation, F sub y equal to 0, this one gonna be 14 kilonewton. Okay. Now we determine the stress. Okay, for sigma sub AB, we will have this one 45.5 and then 10 power 3 Newton, and divide by this one 100. So this is going to be 455 Newton per square millimeter, or this one should be in megapascal. Okay, and that's going to be the stress sigma sub AB occur in this portion. For sigma sub BC, we have this one 14,000 Newton divided by 50 square millimeter, and that's gonna be 280 Newton per square millimeter or 280 megapascal. And then we have what? This one less than sigma sub y. This one gonna be linear elastic portion. And then this one larger than sigma sub y. This one will be in the plastic behavior. Okay, we don't have the answer yet. Then we come to the next one. For this one, we will determine strain based on stress strain diagram. And this one, we will use Hooke's law, okay, to determine it. So, for strain sub A, B, okay, from stress strain diagram, we may say from stress strain diagram, where is going to be 455, that's going to be half of this one, that's 420, 490, they are 70 different, and then we prefer to have half cockpit. This is going to be 455. Then if you do the graph, okay, and then you project it up, you should have put it in this vertical and do it properly. Or actually, you may divide this one by a half. Okay, it should be better. This is, if you zoom it in, divide this one by half. This is about 5 millimeter. So this is about 2.5. Then you may draw the line crosses halfway. Okay, so you get about this one, which is going to be about halfway. Then you project it downward. Then this one not going to be directly related. So you got to extend this one to what? To this one going to be 0.0028, and this one supposed to 0.0032. So in short, you may say this is 0.0030 for strain at A, millimeter by millimeter. Okay, and then come to the second one. We have Hooke's law. We have stress equal to E times strain. So strain sub BC going to be stress sub BC divided by modulus of elasticity. That's going to be 280 megapascal, and then it's going to divided by 290 10 power 3 megapascal, and then you should get the result of this one to be equal to 0.0000966 millimeter per millimeter, or equal to 0.96610 minus 3 millimeter by millimeter. Okay, this one actually 1, 2, 3, 10, 3 times 10 minus 3 millimeter by millimeter. And then if you compare the result, okay, this is going to be 3 times larger than the BC. The blue going to be 3 times larger than the red. Okay, and we put this one, the deformation of this one gonna be based on this one. Okay, and then coming into the total deformation, we have strain equal to deformation divided by length. Then we have the length gonna be strain times L. So we have deformation total that's gonna be equal to the deformation of the AB plus the deformation of the BC, or you may say this is gonna be strain ABL sub AB and then plus strain BC times L sub BC. So it's going to be 0.003 times this one 600. And then you got to have this one plus 0.0000966 times this one 500. At the end, you have the total going to be 2.28 millimeter. And this one gonna be the elongation. Okay, you should get the correct answer, Angelo. Now, permanent set. Okay, after releasing the force. Then after releasing the force, for sure, the behavior of this one will return by this line. And then it's going to follow the linear portion. Okay, linear portion. This is going to be A. This is going to be B, linear portion. And then this is going to be the elastic recovery. This one, we may say this is going to be elastic recovery. And then another portion over here, this is going to be our permanent set. Okay, the green going to be our permanent set. What's going to be this one? The return is linear, so the return gonna Hooke's law, sigma equal to E epsilon. Then we will have strain recovery gonna be sigma over here sub AB divided by the E. Okay, since this is going to recover all the BC, since the BC has linear elastic, when you release the load, okay, the BC recover all, only the AB gonna behave as the plastic behavior, have the elastic recovery and has the permanent set. Okay, then we have this one to be 545 megapascal stress over here, divided by the E to 9010 power 3 megapascal. You should get the strain recovery equal to 0.00157 millimeter by millimeter. Okay, then this is strain permanent. Strain permanent will be the whole strain that we have it. Strain sub AB minus strain recovery, and strain this one is gonna be 3 times 10 minus 3 minus 1 2 3 1.5710 minus 3. So we should have this one to be 1.4310 minus 3 millimeter by millimeter. This is permanent sustain. Okay. Permanent deformation gonna be sustain permanent. And then this occur only for the AB. Take the AB. So we have 1.4310 minus 3 times 600 millimeter. You should get this one 0.86 millimeter. Okay, this is 0.86 and this is gonna be 2.28. You should get 10 points. This one you have learned for 2 times already. Right? Okay. If you laugh, you may not that point. It's okay. It's still the learning process. Then moving to the next one, we come to the three-dimensional stress of stresses. Okay. We have mentioned that in our study, okay, we may use the Cartesian reference one. This is X, Y, and then C. As the engineer master degree, you supposed to be able to draw the cubic, okay, to represent the stress of stresses in 3D. Unlike the previous one, we have only in 2D, but this one is in 3D. What's going to be the stress of stress represent over here? Sigma sub x is going to be the stress act on the surface perpendicular to the x direction, and this is going to be sigma x equal to 10 megapascal. Okay, and then how about sigma y? Sigma y is going to be in the y direction. So this is going to be our sigma y in the y direction. This is sigma y equal to 20 megapascal. And then we have sigma c. Sigma c in negative. Sigma c is gonna be in compression. So this is sigma c equal to 10 megapascal. Okay, Angelo, you should be able to draw the picture like this one. How about tau sub xy? Tau sub xy gonna be stress, the shear stress of her on the surface x and have the direction in the y. This is gonna be tau sub xy, and this is gonna be tau sub yx. And for sure, and this is going to be minus 20. If it's minus, Ajahn didn't put it correctly. Okay, it's gonna be in the opposite direction. It's gonna be in the opposite direction, not in this direction. Okay, and I won't put it in the other side. It's going to mess up things. Be this one and this one. It's gonna be 20 megapascal. If you prefer, you may draw 2 more over here. And then how about tau sub yc? It's going to be on the c-axis and have the direction in the y. Okay, c-axis and have the direction in the y. You can put it over here and then going to have over here and then over here. Okay, and then this is going to be 10 megapascal. The last one gonna be xc, but in the negative direction. xc, cx, but in the negative direction. cx in the negative direction. And then you will see that's gonna be quite messed up. But anyway, test practices. This is 1000 CX and that's 30 megapascal. If you don't it bigger, it's gonna help. Okay. And then following what we have, we got to determine principal, normal stress, and its direction cosine. This is gonna be sigma 1, sigma 2, and sigma 3. And for coordinate direction cosine, only for the sigma 3, that means L3, M3, and N3. Okay, we have noted to determine principal stress, we have the equation from the textbook in the cubic polynomial equation, and that's cubic polynomial equation have this form. That's gonna be sigma n I1 sigma n square plus I2 sigma n minus I3 equal to 0. What could be I1? I1 gonna be easy. Okay, where? Okay, where? I1 gonna be sigma x plus sigma y plus sigma c. Okay, and then let me zoom out a bit. You will get this one 10 plus 20 minus 10. That's gonna be 20 and megapascal. Then for the I2, you also have the equation that's gonna be sigma x times sigma y plus sigma y times sigma c plus sigma c times sigma x minus tau sub x y square plus tau sub y c square plus tau sub x c square. I don't put the number. Okay, you should get this one to be minus 1,500. I should say megapascal square. Okay, and then the third one actually is better to put it in matrix and use determinant to determine it. The I3. Okay, I won't put it in this detail. We have sigma x, sigma y, sigma. Well, that's quite a lot. It's okay. Plus 2 tau sub x, y, tau sub y, c, tau sub x, c. And then minus tau sigma sub x and tau sub y, c square plus sigma sub y, tau sub cx square plus sigma sub c tau sub x y square, those kind of things. And this is gonna be minus 5,000. The unit gonna be this one cube. Then we have what? We have sigma sub n, and then this one minus 20, and then this one 20 sigma n cube, sigma n square, and then minus 1,500 sigma n, and then minus of the minus 5,000 and then equal to 0. You put into your calculator, you should get sigma 1 equal to 48.695 megapascal. And then sigma 2, okay, that's gonna be 3.218 megapascal. And sigma 3 gonna be minus 31.91 megapascal. That's gonna be the stress of principal stresses. Okay. How about the direction? They ask us only direction related to only sigma 3, not the whole one. Okay, only sigma 3. So you may take only two equations. Okay, for example, you may take only sigma x minus sigma 3 and then L3. Okay, and then plus tau sub x, y, and then M3, and then plus tau sub xc, N3 equal to 0. Okay, another one, you may use tau sub x, y, L3, and then plus sigma y minus sigma 3, M3, and then plus tau sub yc n3 equal to 0. And then one of important thing, L3 squared plus M3 squared plus NT squared equal to 1. Okay. Following this one, you got to put everything in order. 10. Sigma x equal to 10. Minus of the minus. Minus of the minus. Right? 31.91. And then L3. And then you have what? XY. XY over here. Okay. Minus 20. And then M3. Okay. And then this one plus plus this one. Tau sub xy. Minus 30 minus 30 N3 equal to 0. Okay. And then tau sub xy minus 20 L3 plus sigma y 20 minus of the minus 31.91 M3, and then YC is here plus 10 N3 equal to 0. So based upon this equation, you may rewrite the equation by divided by N3, right? This one gonna be 41.91. This one gonna be 41.91 L3 over N3 plus 20 M3 over N3 equal to 30. And then another equation gonna be minus 20 L3 over N3. And this is gonna be what? Plus 51.91 M3 over N3, and then minus 10. You may solve it, okay, for the result. You will get L3 over N3, okay? L3.
About 20 is minus 20.
This one?
About
This one. Oh, yep. This is going to be minus 20. After you solve this 1, 2 equation, you will get the ratio of L3 over N3, right? And then later you put it over here. You will get L3 equal to 0.605. And then M3 0.081. And then the last one, N3 0.792. Okay, that's going to be the result. Okay, this is going to be the coordinate direction cosine. Okay, coordinate direction cosine. And then can you determine alpha 3 equal to degree? Okay, alpha 3, beta 3 equal to degree, gamma 3 equal to degree. I didn't ask in the question, but you may determine the angle by yourself. Okay, and that's going to be the angle LT with respect to X, Y, and Z. Now, coming to maximum shear stress is better to draw the diagram. Okay, the diagram. And then we should have the more circle to represent it. And then we may put this one, 1, 2, 3, 4, 5, 6, okay, and then this is going to be plus stress. And then this is going to be minus 10, minus 20, minus 10, minus 20, minus 30, 10, 20, 30, 40, 50, 60. And this is going to be 1, 2, and then 3. And then we have 3 stresses. One going to be 48, about this one, 48.695. And then another one, 3.218. This is 3.218. And another one, minus 31.91. That's going to be over here. Minus 31.910. Okay. And what's going to be halfway of this one? Sigma average of this one going to be what? 48.695 plus is my what do you get? 8.4. That's going to be about this one. Then you draw your more circle of the first one. You have this huge more circle that's supposed to cover everyone. Okay. And how about this one? It's going to be 30 to 35, 17 something. I think it's going to be about this. This is going to be your more circle. And then you should have another one that's going to be 45. It's going to be 20. Something like this one. Okay. Okay, it's going to be this one. Now, you get the center of this one, you get the center of this one, and you get the center of this one. For this one, you will use to determine tau max. That's going to be tau between 1, 3. Okay, and this is going to be tau of the 1, 2. And this is going to be tau of the 2, 3. Okay, so the maximum shear stress and average normal stress, the first one, sigma average 1, 3. That's going to be sigma 1 plus sigma 3 divided by 2. You should get this one, 48.695 plus 31.91 divided by 2. Okay, and this is going to be 8 point something. No, it's going to be yep, it's incorrect. This is negative. 8.4 what? 392. Okay, and then you may determine tau. Okay, that's gonna be sigma 1 minus sigma 3 over 2. Okay, that's gonna be tau 1, 3 absolute sigma 1 minus sigma 3 and then over 2 and that's gonna be absolute 48.695 and then plus 31.91 with the absolute and then divided by 2 you should get this one 40.3 megapascal. Following what Ajahn show you over here, this is going to be sigma average 1,3 and tau 1,3. You should get this one equal to 8.392 and 40.3 for this one. And then do the same thing for sigma average 1, 2. That's sigma 1 plus sigma 2 divided by 2. 48.695 plus 3.218 divided by 2. That's gonna be sigma average for this one. And then tau 1, 2 is over here. It's gonna be absolute sigma 1 minus sigma 2 divided by 2. That's 48.695 minus 218 divided by 2. You should get this one. Sigma 1, 2. 22.74 megapascal. And the center gonna be 25 .956. This is going to be sigma average 25.96 and 22.74. Okay, and then you get the result. Check it. The third gonna be the same. And then this is going to be our B. Okay, this is going to be our A. And then for our C. And then for the result, another one going to be 17.564. Yeah. And then the last one, we got to determine sigma octahedral. That can be determined from 1/3 of sigma 1 plus sigma 2 plus sigma 3 or equal to 1/3 sigma x plus sigma y plus sigma c. The same. You will get the same. That's gonna be equal to 20 divided by 3. That's gonna be 6.67 megapascal. This one will produce only change in the volume. Okay, change the volume, not change the shape. Then we have tau octahedral. It's up to you how to determine it. Tau octahedral. You may put it by equal to sigma 1 minus sigma 2 square plus sigma 1 minus sigma 3 square plus sigma 2 minus sigma 3 square. And that's going to 9 equal to tau octahedral square. Okay, put everything together. You should get tau octahedral to be 33 megapascal. When you get score, you get very beautiful score. So provide the score. Okay, that's 3 plus 5 plus 3 plus 2. That's gonna be 10 points. Okay, mark it. We finish another one on this one. Now, come to this one. This one may be a bit of problem to draw the free body diagram. We will draw free body diagram. Okay, of the bar and determine the internal forces and moment. Okay, internal forces and moment. Now, the force he applied to the L-shaped bar with the solid cross section. That means it's going to have this kind of section. The force Px normal in the plane of the bar. That means the force P is in C direction. Okay, force P in C direction. If the material is isotropic and have sigma sub y equal to 28 megapascal, they ask us to determine, this is analyze, determine the P that will cause the failure based on maximum shear stress criteria and maximum octahedral shearing stress criteria. And what the assumption to be used? For sure, assumption under the applied force, the behavior of the material must be in linear, elastic, and then with small deformation. Okay. And the P, the material has linear, elastic behavior and small deformation. Okay. Then how to draw the free body diagram? Okay, let us work together. Okay, you may make a copy, Angelo. Okay, you may make a copy. This one. Just take this one by, let's see, this one. Take this one by 7. Okay, this one by 7. This one supposed to be over here. And then this one by 7, this one by 7. The origin must be here. And then we have this one for positive C axis. And then this one for 7. Just put this one for the positive X. And then this one for the 7. Okay, you may put again this one for plus Y axis. And then we have the section over here and dock it. And then dock it, make a copy. And then this one for 7 and this one for 7. We have circular section over here, draw the line link over here, and then draw the line link over here. In my generation, make a copy is our duty. Now, following what we have here, we got to have the reaction. And again, the reaction must be the force. This is going to be the force. Let's put it. This is point A sub Y. And then this one should be A sub X. And this one should be A sub C. Okay. And then also over here we should have this one, the moment M sub Y. And this one supposed to be M sub C. And this one may be M sub X. And then follow what we have, the force over here for P. Summation of F sub C equal to 0. Then A sub C upward. positive, A sub C will be equal to the force P. This one will opposite equal to P. How about summation of F sub X equal to 0? There is no force in X direction. A sub X equal to 0. No force in the X direction. Okay, and then summation of F sub Y equal to 0. No force in Y direction. So A sub Y equal to 0. A sub Y, A sub X equal to 0. This is P. Okay, this is P. How about the moment? Okay, we have P in C direction. Actually, this is important. We have P. The P is in C direction. So no M sub C. Since parallel. Okay. Since they are in parallel, and then no moment arm. Now in parallel. So M sub C is gonna be 0. This is 0. Now thinking about this one. See this one. This is gonna be in. Okay. Is going to be y-axis. The same thing. This is going to be the connection like this one, angular, like this one. This one gonna be go. This one going to go together. Okay, in this direction. And let me zoom out. Okay. Then the force P putting in this direction is going to twist this one about y-axis in this one. And then it's also trying to twist in this direction. Two way. One is going to twist this one. Okay, so it twist this one in y direction. And then it's also going to twist in this one in the x direction. In the x direction, it's gonna have the distance here. This is rotate in the x direction. And rotate in this direction. Is required moment arm over here. This is gonna be about y. This is gonna be 80 millimeter. Okay, and how about this one? This is gonna be 50 millimeter. 80 millimeter will about this axis. Okay, and 50 millimeter is gonna be rotated about this axis. So summation of F sub X equal to 0. M sub X equal to this force P times the distance here. That's going to be 50 times P. Okay, in the P direction. Okay, and then that is this way. In this way, this is in Y direction. Summation of M sub X, summation of M sub Y equal to 0. M sub Y going to be equal to 80 times P. Okay, so this is only M sub Y equal to 80 times P. M sub X is going to be 50 times P. Now, we got to consider the stresses, okay, due to the moment and torsion. We consider the stresses due to, I should say, M sub X is going to be bending moment. Okay, and M sub Y will equal to torsion No moment. Okay. And then how about the shear force? Shear force. Shear force of what? Shear force of A sub C. Okay, A sub C. A sub C. Now, if you consider the shear force of A sub C is will tau equal to VQ over IT. Okay. And for the M sub X, you will have sigma equal to M sub X. Okay, times Y over I. And then for M sub Y, you will have tau equal to M sub Y. Over J. Okay, we are going to have three equations. But most of the time, I should say, most of the times, okay, the tau due to shear force, is significantly smaller than tau equal to the torsion TR over J most of the time. Okay, so we may neglect the tau equal to VQ over IT. Okay, we neglect it. Neglecting. Okay, tau equal to VQ over IT. Now, coming into the section, it's going to be three dimension, right? So we will have this one, we will have this one, and this one. For this one, Ajahn should say this is X and this is C. Okay, this X is C. We're going to consider mainly this one, and then this is going to be in Y direction. Then, due to the bending moment over here, okay, this is going to bend about this one. The moment resisting going to be in this direction. So, in this one, we will have the compression in the top, and we will have tension in the bottom. This is going to be the normal stress. Actually, it must be equal. It must be equal. And then for the, again, shear stress due to this one, due to the torsion, we will have this rotation in this direction. So the resistance gonna be in this direction. And Ajahn should say that the stresses gonna be smaller and smaller, have this kind of distribution. Okay, and how about this one? Shear of this one will be quite complicated. Along this one, it's going to be curved like this one, curved like this one, but usually it's small. So we put this one approximately equal to 0. Now, what we have is going to be the stress. This one going to be sigma in y direction. Okay, this surface is perpendicular to the y-axis. The rotation is going to be allow this section. If we put this one in x. This one will be tau sub yx equal to tau sub xy. But if you project it over here, okay, it's going to be tau sub y x, okay, y in x direction. But if you put it over here, this one will be tau sub y c is perpendicular to y. Okay, direction is in c direction. Is perpendicular to y. The direction in x direction. So depend on what you would like to use. But this one no change because this one only in the y direction. So sigma sub y equal to moment this one m sub x. Measure up, measure down. That's gonna be c, and then divide by moment of inertia I sub x. Then this is pretty tough. It's okay, but this is going to be 50p. Okay, 50p. 50 in millimeter. Okay, time p. C. You measure this one up. Okay, and then they didn't tell us about the diameter, right? And this is a 4 again. Angelo, we need to check this one. I can make a mistake. There is no diameter. This one. Oh, the figure. Okay, over here. This is 6 millimeter. So it's gonna be 3 millimeter. And then divide by moment of inertia of the section pi, and then 4, and then 3 millimeter power 4. Okay, and then you should get this one 2.36 T. Okay, and everything in millimeter. How about sigma sub y c? Okay, it's gonna be m sub y, and the radius is gonna be r over j. Again, this is gonna be 80 p. The radius is gonna be 3 millimeter. J is gonna be 2i because j is I sub x plus I sub y. They are circular, so they are equal. So pi over 2, and then 3 millimeter power 4. So this one you get 1.836 p. Okay, then this is going to be the stress. Okay, if we select YC is not correct. It should be YX. This one is not because stress here gonna be 0. Sorry, this is gonna be YX. The element gonna be at this point, and then at this point, at the bottom point, subject to tension and subjected to shear stress here. So principal stress, that's gonna be sigma 1, 2, gonna be sigma x plus sigma y divided by 2 plus minus square root sigma x minus sigma y, and then square plus tau sub xy square. And then again, following this one, we have only sigma y 2.36 p divided by 2 plus minus square root of 2.36 p divided by 2 square, and this one plus 1.8 T6 T and then square root. Okay, so we have sigma 1 equal to 3.41 T and then sigma 2 gonna be minus 1.05 T. Now, depend on failure criteria that you use. Okay, if you use maximum shearing stress, now sigma 1, only sigma 1 we have, and then sigma 2 negative. They are opposite side. When they are opposite side, we will use sigma 1 divided by sigma y minus sigma 2 divided by sigma y absolute and put it equal to 1. Okay, and now we have 3.41 P over 280 minus of the minus 1.05 P divided by 280 and then put it equal to 1. So P gonna be 62.8 Newton. Since this one is in Newton per square millimeter, this one in Newton per square millimeter, this equation in millimeter. So P gonna be in Newton. If you use maximum octahedral shearing stress, okay, that's gonna be sigma 1 divided by sigma y square minus sigma 1 over sigma y, sigma 2 over yielding stress, then plus sigma 2 over sigma sub y square equal to 1. Then 3.41 P divided by 280 square minus 3.41 P divided by 480 and sigma 2 minus 1.05 P divided by 280 and then plus minus 1.05 P divided by 280 squared equal to 1. Then we have P equal to 69.2 Newton. That's quite a lot, Angelo. I don't know. You get how many score on this one? Okay. And submit it to me later. Okay.
I'm not something wrong here. It's the same way.
The same way.
The same
But
way.
how about the result?
Distortion energy.
Okay.
You use the distortion energy.
And yeah, the distortion energy and octahedral shearing stress is the same one. The same one.
I should get the same, but the moment are I switch the 50 and 80.
Keep your own score. Okay. You mean you have a mistake on the engineering static and mechanics of materials, so keep your own score. Okay. Then we have the last one over here, and I think you may saw this one, have the pictures, and that should not be that tough. Okay, the shaft, okay, now have 20 millimeter diameter, made by ductile steel, have sigma sub y here, subjected to the force P over here of 25 kilonewton. M sub x over here is going to be 50 Newton meter and torsion 120 Newton meter. The same thing. Okay, you may think this is B. This is B. You may cut the section and then draw B body diagram of this one. Then that's going to be the section. Now, do a copy of it. Okay, make a copy of it, put it back over here, and this is going to be your point B. Point B. Now, thinking about the force over here, 25 kilonewton. Okay, the 25 kilonewton will provide the uniformly distributed stress all over the section, and then sigma equal to the internal force P divided by A. Okay. Now, how about M sub x? Do the same projection. M sub x. And this is going to be the surface. Okay, this is going to be your shaft. And now, M sub x, if you put it over here, M sub x gonna rotate in this direction. Okay, it will resisted. It in this direction is will resisted by another moment in this direction. Okay, and then this is your point B, and then your point B is going to be at this end, not on this end. So for sure, this is going to have the tension, and then this gonna have your compression, and this gonna be your stress distribution. Okay, on this one. And then on the third one, we have this one, and you have torsion for now. Torsion over here. This is 50 Newton meter. It's going to resist by the moment over here, 50 Newton meter. For the torsion, you will have this torsion, that's 120 Newton meter. So this is 120 Newton meter. But thinking about this section, you will have the shear stress distribute along this one and have zero over here. And this is your point B. This is your point B. And this is your point B. Okay. Your point B, sigma sub B, will subjected to P over A. And also over here, it will subjected to the tension. Plus, it's going to be M sub x. And this is going to be radius and divided by I sub x in this direction. Okay. And then the problem said determine the factor of safety for the design based on octahedral shearing stress criteria, the same as the maximum distortion energy in kilogram. Now, you got to put safety factor and safety factor over here. And for this one, let Ajahn put this one. This is going to be SF. And then the force P that's resist over here gonna be 25 Newton. And then the area gonna be pi r. This is diameter. So pi times 10 millimeter square. Okay, then Ajahn plus SF and then time m sub x. This is 50 Newton meter. Okay, you got to time it by 1000 to make it to be Newton millimeter. And then we have the radius again. That's going to be half of this 10 millimeter. And then we have I sub x. Oops, sorry. I sub x. I sub x of this one. Pi over 4 radius. Power 4. Right? This is going to be pi over 4. And then times 10 millimeter over 4. If you need correct, everything supposed to be correct. This is gonna be safety factor, and then time 143.24. Everything in the unit of Newton and unit of square millimeter or in megapascal. Okay, and then we have tau sub b over here. This is shear stress. And then that's gonna be equal to safety factor time moment. That's gonna be PR over J. That's gonna be safety factor time 120 Newton meter time 1000. Change the unit change it to Newton millimeter. Then the radius is gonna be here, gonna be 10 millimeter, and then J is gonna be 2I sub x. Okay, and then you divide it by pi over 2, and then 10 millimeter power 4. Everything put it together. You have SF. Time 76.39. Okay. Okay. Then you have what? You have use maximum octahedral shearing stress. Okay. You have how octahedral. It depends on what you use. This one you didn't determine. Sigma 1, sigma 2, we didn't find it. So our tau octahedral supposed to be in the form of sigma x, sigma y, sigma c, those kind of things. So it's gonna be 1/3 square root of sigma x minus sigma y square plus sigma x minus sigma c square plus sigma y minus sigma c square, and then plus 6 tau sub xy square plus 6 tau sub xc square plus 6 tau sub yc square. Okay, and then our element is going to be over here. Okay, the stress is going to be actually the stress. This is element B. The stress is going to be in this direction, and that's going to be in this direction. Sigma sub B equal to sigma sub C. And then the shear, okay, the shear in this direction produced in this direction. This is perpendicular to C. So tau sub C in the direction of X, tau sub CX is not X. So you have this one, and then this is no. This is no, only XC and CX, and then this clear. reduce this one is going to change to 1/3 of the square root. This one, sigma sub c square. This one, plus sigma sub c square, plus 6 tau sub xc square. Okay, our equation reduced to this one. This one. And then, as you may know from our chapter 5, tau octahedral for the testing is equal to square root over t sigma sub y. So this is going to be square root 2 over 3 sigma sub y. This one cut. This is the yielding. Okay. So we put the yielding over here. Square root 2 times 400. This is in Newton per square millimeter equal to square root 2 times of this one of SF, and then 143.24. Okay, and then all of this one square, and then for this one plus 6 and tau sub cx or xc SF 76.39 square. Now you reach to the point that you may solve. SF gonna be 2.05. What did you get, Angela?
2.05.
Oh, fine, okay, perfect. Okay, if you can do so. That's from our textbook. So that's all for the midterm examination. You should give your score and submit your work back to me. Okay.